And very good day. So we're going to continue our next chapter, which is chapter 7. Okay. So in this chapter 7, we will cover about series and parallel pipeline system. Okay. So the aim of this chapter is that you will be able to explain what is the class 1, class 2, and class 3 series of pipeline system. Okay, and you will be able to explain what is two branch and three branch parallel pipeline system. Okay, so for this chapter is quite relaxed because that there is less of calculation or formulation step. Okay, because you already covered that thing in a previous chapter, which is chapter 6. Okay. So in this chapter, we're just gonna categorize the pipeline system. Okay. So this is the topic that I'm gonna cover for this chapter. First of all, I will explain to you what is the series pipeline system, and next, you'll be able to identify or to classify the series pipeline, whether it is class 1, class 2, and class 3 system. And after that, we're going to discuss what is parallel pipeline system. And under pipeline system, we're going to discuss about two branch and three branch system. Okay, don't you know that? Okay, in many piping system, okay, it's involved actually more than one pipe. Okay, so for example, if you look at this picture here, it is a pipeline which is involved in some of the chemical production line. Okay, and here, in fact, for plant irrigation system to produce vegetables, okay, it also involves more than one pipe system. Okay, so actually, the way to arrange the pipeline system, it has certain categories. Okay, it has a certain types. Okay, so most simplest multiple pipe system basically can be classified into these two main categories, which is whether the pipe was arranged in series pipe system or the pipe was arranged in a parallel pipe systems. So what is the difference between series pipeline systems and parallel pipeline system? I think it will be easier for you to understand that arrangement by just looking at this picture. Okay, so if you look at here, this one is the series pipeline system. Okay, so just the flow is just gone through a straight line, okay, without being divided into any junction. Okay, but here for parallel pipeline system, okay, the flow here is divided into few pipe. Okay, so for example, like this one, it has three branches. Why you call it as a three branches? So from one junction, okay, it breaks into 1, 2, and 3. So that's why you call it as a three branch system under parallel pipeline system. Okay, you may also break it into two branch like this. Okay, so from one sources, you may break it into 1 and 2. So if it's like this, we call it as a two branch, and if it's like this, we call it as a three branch. And for series pipeline system, it has three main categories, which is class 1, class 2, and class 3. So what are the difference between the different classes? We will discuss on the next slide. Well, if you look at the picture here, it shows one of the example or arrangement of the pipe, which is arranged into a series pipeline system. Okay, so what is the series pipeline system? Okay, so basically for series pipeline system, okay, the fluid will flows into a single flow path throughout the system. See, it just has one single flow path, okay, throughout the system. And then So the pipe is connected into series. So for example, we have 1, 2, 3. So it been connected into three into in a series arrangement. Okay, so the flow rate through entire system will remain constant and regardless what diameter which is changed from this point into another point. Okay, so it's not depend on the um, diameter of the individual pipe system. So when we're talking about the head loss, okay, throughout point 1 until point 2, it can be explained from this equation. Okay, so for example, you want to know what is the head loss occur between point 1 and point 2. Okay, so from point 1 to point 2, it has two categories of pipe, which is A and B, because it has different diameter. Okay, it has DA and DB. So um, the head loss is actually the summation of head loss or energy loss in A, HLA, and the head loss in B, HLB. Okay, so that's why the total loss from 1 until 2 in a series pipeline is considered as HLA plus HLB. Okay, so this is what I mentioned just now. The total head loss is actually equal to the sum of the head loss in individual pipes. Okay, so this is the individual pipe, part A and part B. And also including the minor losses along the pipe. So for example, if between A and B, we have valves, okay, so we have to include the loss between along it, okay. And the longer the flow path and the more device passing through, the more energy loss from the system. Okay, so the energy loss here, okay, is strongly influenced by the length. Okay, so for example, the longer the flow goes, it will increase more losses, and if it goes longer, it will pass through many um, equipment or devices, such as we have loss in valve or fitting or bands, okay, and the surface friction. Okay, okay, so as I mentioned just now, for series pipeline, it has three main categories, which is class 1, class 2, and class 3. So what are the difference between these three different classes? Okay, let's take a look at the first classes first. Okay, so usually for class 1 pipeline system, series pipeline system, okay, the system usually it defined as the size of the pipes and the types of minor losses that are present in the system and the volume flow rate of the fluid in the system. Okay, but for class 2, okay, usually system will give information about elevation, fitting, size, valve, and fittings in the system, and pressure at any point in the system. Okay, but for class 3 is more on the complicated system, which is the application. Okay, so usually it gives all the general layout of the system and the desired volume flow rate that um, is known. Okay, that's mean the volume flow rate is known or is given in the system, and general layout is completely provided. Okay, so what is the objective for class 1, or usually what you asking to do in class 1? Okay, so in class 1, maybe you'll be determine the pressure at any point of interest. Okay, maybe point 1 or point 2. Okay, depends on the question. And maybe you'll be asked to calculate the total head of the pump, or maybe you need to calculate the elevation of a source fluid, or maybe you'll be asked to produce a desired flow rate or pressure at a selected point in a system. Okay. Meanwhile, for point 2, it's more like once you to know the volume flow rate at the of the fluid that could be delivered by a system. Okay, and for class 3, okay, you may be asked to determine what is the required size or the correct size of pipe which is need to be used to carry a liquid at a certain flow rate. Okay, so in summary, we can say that this one is more on very basic or very theoretical. Okay, and this one is more like application level. Okay. So what is parallel pipeline system? Okay, so it may look like this. It is look like this. Okay, so for example, from one sources, you have a junction and then you will divide the flow into two or three or more channels, okay, or more flow paths, okay. It's different to the series, in which that for a series you just has one single flow path for the liquid to flow, okay, but for parallel it has two or more. Okay, so at this juncture it will distribute the flow into many flow paths, okay, two, three or more, so it called as a parallel pipeline system. Okay, and it will join again at another junction at the end here. Okay, so here we have the definition, which is that parallel pipeline system are those having more than one path. Okay, as I told you just now, it has more than one path, part 1 and part 2, or maybe 3, 4, okay, for the fluid to take as it flows from a source to a destination point. So it has its own destination point. Okay. So for a parallel pipeline, okay, it has two categories. Okay, actually it's more, but for your level, we're just gonna cover two categories, which is two branches and three branches. If it's more than three, it is a complex pipeline system. Okay. Okay, so now we will see what is the theory or equation or formulation involved in the parallel pipeline system. Okay, so here the first concept is we know that the total flow rate, okay, at a junction in downstream is actually the summation of flow rate in the individual pipe system. Okay, so for example, the total flow rate here, down here, okay, is actually QA will be equal to the summation of the flow rate in Q1 and Q2. So this is Q1 and Q2, right? And the pressure drop for each individual pipe must be the same, okay, must be equal, okay. So what happened is the delta P, okay, in part 1 here, the delta P here and delta P here should be the same, okay. So therefore the P1 will be equals to P2, or PA will be equals to PB, okay. So for example, here is B, so PA will be equals to PB. And here is the derivation of the formula for the head loss. Okay, we will see that since that the pressure drop is the same, so that's why the head loss, okay, is the same. Okay, so that's why the head loss in part 1, which is at this part, okay, the head loss here is equal to head loss in 2. Okay, so in this part also the same value as here, the head loss there. Okay, so therefore we can rewrite the equation. This is the equation for head loss, okay, for part 1, and this is the equation for head loss in part 2. Okay, So since we know that the head loss for each part, okay, part 1 and part 2 is the same, so we can make the equation like this for head loss, okay, and we know that we can also be rewrite into this form. This is a term to calculate the head loss for each part, okay. So therefore, from this equation, we can make a ratio of the average velocities and the flow rates in each two parallel pipes. Okay, so we want to know what is the ratio in part 1 and part 2, so that we will arrange this equation. Okay, so we will bring all the V1 over V2. Okay, so it is become like this. This is the ratio for between V1 and V2. And we also can write it into another form. Okay, so this is the ratio in terms of velocity, and this is the ratio in terms of the flow rate. Okay, just been multiplied with the A here. Okay, so you may get the flow rate ratio. Okay, so if you look at here, what's the difference is you just multiply with the d to the power of 2 for each pipe. Okay, and then because here you add the A, and therefore in another second term here you need to add the d1 to the power of 2, d1 to the power of 2, because we know that A is actually pi d to the power of 2. Okay, so pi can be cancelled because it's a constant. All right. Okay, so as a summary for parallel system, okay, I can write it into two simple concept. Okay, two simple principle. It doesn't matter how complex is the arrangement of the parallel pipelines. Okay, the first one is the conservation of mass throughout the system must be satisfied. Okay, so concept of the mass conservation, which is Q in equals to Q out, should be satisfied. Okay, so here it's stated clearly. It says that this is done by requiring the total flow into a junction should be equal to the total flow out from the junction, okay, regardless of the change in diameter along it. Okay, so for example, the junction 1, which is a Q in, okay, should be equals to Q out. The flow rate at the in junction should be equals to flow rate at the out junction. Okay, and then the pressure drop between two junctions must be the same for all paths between the two junctions. Okay, so the delta P should be the same for all the paths along the system, between the two junctions. Okay, so this is because that the pressure is a point junction and it cannot have two values at a specific point. Okay. Okay, so let me show you shortly what's the difference between two branches parallel system and three branches parallel system. Okay, so for example, this is the application of two branches parallel piping system. Okay, so it's actually we use this parallel pipeline system because we want to isolate the heat exchanger so that we will allow the continuous flow while the equipment is serviced. Okay, so here, as you can see here, okay, we want to isolate this heat exchanger. So that's why we have this kind of continuous flow occur here. And of course, we need a gate to control the flow from in and out of this heat exchanger. So we require a gate valve here. Okay. Meanwhile, for three branches, okay, or if the system has more than three, okay, for example, it has like 3 or 4 or 5, okay, we call it as a network. Okay, so I think it's very easy, pretty easy for you to recognize whether it is 2 branches, 3 branches, or more than that. okay, or network piping system. Okay, so oh yeah, we come to the end of this chapter. Okay, so before we end, let us test yourself. Okay, let me test ourselves. Also, the knowledge that we have gained along this video. Okay, so for example, by looking at this system, okay, we want to move the liquid from tank A and it flows into a a reservoir B. Okay, so there are piping system involved along point A to point B. Okay, so first question, okay, so let's write the general energy equation for the system involved in this figure. Okay, so I hope that you still remember about the energy equation. Okay, and of course we have lots of devices and piping arrangements that may contribute to head loss. Okay, so I hope that when you consider about energy, writing about the energy equation, you consider about the energy loss inside the system, which is shown in this figure. Okay, and the second one is you need to identify 6 factors that contribute to the total energy loss in the system. Okay, so let's try. Okay, so first thing you need to write down the energy equation which is involved in the system. Okay, so energy equation is that the extension of the Bernoulli's equation. So here we have 2 points, okay, point B and point A. So just identify what are the equation may involve. Okay, so this is actually um, the equation, the Bernoulli equation, which is involved in part A. Okay, so at the end, basically it's just like this, but we have to consider the energy loss. That's why here we include minus HL. Okay, because uh, the loss, okay, that may occur along it may contribute to the energy loss, okay, inside the system. And we knew that, okay, so VA here and VB here will be 0 because it is at entrance and exit, due to entrance and exit loss. Okay, so the PB here we consider is as a 0 because it's just open. Okay, it's not been sealed. Okay, so next part. Okay, so this is actually the ultimate, okay, of this knowledge that we have covered in chapter 6 before, so that we combined it and test yourself here. So if you look at here, this is the arrangement of the piping system is actually in a series system, yeah. Okay, it has no junction at all. Okay, and then what are the 6 factors that contribute to the energy losses? Okay, so let's take a look. Okay, so first of all, it has exit loss. So can you identify where is the exit loss? Okay, so I repeat again, the flow is actually from tank A and it flows to tank B. So it may have the exit loss at which point? Can you identify where is the exit loss occur? Okay, so there you go. It's just by here when the liquid just about to exit or to leave the tank A, okay, before it enters the pipeline. And then the swing type check valve. Okay, so then the liquid will go through the swing type check valve here. So it will cause the energy loss due to the valve. And then it will goes to the angle valve here. So it also contributes to the another energy loss. Okay. Then it has elbow, 90-degree elbow. Where is the 90-degree elbow? Here. Here is our elbow. Okay, and then before it entered the reservoir B, it has entrance loss. Okay, here is the point where we have the entrance loss. And lastly, the friction, okay, the surface friction, which is occur along the piping system. Okay, from this point to this point along here, it has a pipe surface friction. Okay, that's it. So we come to the end of this chapter 7. Thank you very much. See you again.